So welcome everybody. My name is Johannes Veh and I will tell you something about file systems and efficient data handling. And as you may know, this is a rather important topic for us because from time to time we see issues with file systems, sometimes because something in the file system went wrong, oftentimes because some user is doing things which the file system was not designed for. So let's talk a bit about what our file system can and cannot do and learn what we can do better in the future to not overload file systems. But before we get started with file systems themselves, we have to think about what the hardware is underneath. So you may have seen these building blocks in your local machine, your notebook, your computer. So we have HDDs. These are spinning disks. It's a technology which is a few decades old, quite reliable, cheap, but slowish because there's a rotating disk inside and the reading header has to get to the point where your data is. So you have to wait one entire spin before you can read data. You have to wait an entire spin before you can write data. So it's slowish. Then we have SSDs. I think this technology is about 20 years old or something like that. You probably have heard about them. And we have the NVMEs, which is basically SSD on steroids. They are about a factor of 10 faster. And yes, and this is, so the NVMEs is what you probably have in a modern notebook on your desk when you're working. And our storage systems are built from these disks as well. But as you may know, a single disk has a quite limited capacity. So we don't use a single disk. We use a few hundred of them and build several racks of storage. So what you can see here are two pictures of the storage array, which is underneath /home HPC and /home vault. So this is our main storage, let's call it like that. And it consists of roughly 1,000 HDDs, 20-ish SSDs, and it almost weighs 3 tons. Okay, so what we do by building a storage array out of these many disks is we increase capacity. We somewhat increase speed because we now have several disks which can all read at the same time and write at the same time with some limit. So scaling is not with the factor of disks, so we don't get 1,000 times faster than a single disk. We get maybe a factor of 10 or 20 or something like that because there's a lot of software between to get all these things done. So we are still slowish because it's HDDs, it's not SSDs. And building something like this entirely out of SSDs would be quite expensive, so we don't do that. Okay, so this is the hardware underneath. So what about file systems? I said I will talk about file systems. So a file system is a directory structure. And you know this, again, from your local machine, from your laptop. When you're running the Windows, you have these letters, C, D, whatever, depending on how many file systems you have. In Linux, they don't get assigned letters, but a more or less random name, which we can choose. And they are mounted somewhere in your directory structure. So for us, the file systems, which are globally available, so on all machines in the HPC ecosystem, all these file systems have something like /home/ some name. And then we have a few, let's call it special purpose file systems, which don't follow this naming scheme because they have limited access. So they aren't available on all our systems, but maybe on a single cluster or maybe on a single compute node. And so a file system can vary in size, in speed, in all kinds of characteristics, depending on which kind of hardware is underneath and also which kind of software stack is running. Okay, so let's have a look at the file systems we have available here at NHR FAU. So as I already mentioned, we have home HPC. So this is your main home directory. It has a very high data security. So we have backups and snapshots. I will come to that in a moment. The data is stored there as long as your account lives, plus a few days. And the quota is rather small with 50 gigabytes. This is simply because of the fact that backup and snapshots are somewhat expensive, so we can't give you infinite space on this file system. Then we have Home Vault. This is also somewhat secure, so also quite secure system with backup and snapshots, less frequent than Home. So here we do it only daily, not twice an hour. And your quota is a factor of 10 larger, so half a terabyte. And the data also lives as long as your account is available on the systems. Then we have our work systems. So here they are several file servers. So these are not a cluster as I showed before on the slide, but a single server with some disks inside. They are Woody, Saturn, Titan, Arduino, and Janus. And they don't come with backup or snapshots. So if you delete something on these servers, it's gone. For the other two, you can retrieve it from backup or snapshots. You have an even higher quota. So for tier 3 accounts, it's 1 terabyte. And for NHR projects, it's a project quota, so not a single user quota as in all the other cases. And this quota varies depending on your application. Okay, and all these systems I talked about so far, they are made of HDDs. So they are somewhat slowish, but cheap. So this is why we buy them. Then we come to the systems which are not available on all our compute nodes or in all our ecosystem. So we have Lustre, which is a fast parallel file system available in Fritz and Alex, so only in the newer clusters. And this file system is built for parallel I/O, so for code which runs many threads which need access to a single file or a low number of files. You don't have a quota on this system. There's only deletion if the system gets too high. You will be notified, so we don't delete data without telling you that we have to somehow get rid of something because it's filling up too much. But there's a limit on how many files you are allowed to have on the system because it's designed to have a small number of files. And as soon as the number of files in the systems gets too high, it slows down quite dramatically. And then we have NVMe. So this is, as you may have guessed from the name, not a storage based on HDDs, but made of NVMe disks, so solid state disks. This is also available on Fritz and Alex, and it's specially designed for small files with rapid I/O operations. So touching a file, writing a single number, just reading small files. So the typical machine learning workload. Yeah, there's also no quota on the amount of data you're allowed to have. There is a file quota, so how many files you're allowed. I think it's 5 million or something like that. So it's quite high, but there is a limit. And data is there as long as your workspace is allocated, and I will come to workspaces in a moment. And then we have temp directory. This is a single disk inside your node. So just one of these disks I showed on the first slide. And depending on the generation of the node, it's an SSD or an NVMe. So the older nodes have SSDs, everything newer is with NVMEs. And in some rare cases, this disk is not. So the temp directory is not a disk, but a part of the main memory of the node. And data which is copied there will be gone at the end of a job. If you write something to this disk, make sure it's copied away if you need this anymore. Okay, so I told you I would come back to backups and snapshots. So backups, at least for our systems, are basically copies of the data which is written to a completely different system, so a tape system. And you as a user don't have access to this backup. This is something only we as admins can do. But we have snapshots which basically cover the same data and the same historic range, let's call it like that. And this is available Home HPC and Home Vault. And you can simply go to the snapshots by typing cd point snapshots, and then you end up in a directory which looks something like that, probably is new timestamps. And this is basically the timestamp when a snapshot was done. And then you can enter this folder and copy back whatever file you accidentally deleted or have overwritten, or whatever reason that you need the old version of a file. Okay, the next thing I mentioned is workspaces. So workspaces is basically something the HPC community came up to produce temporal directories with some kind of management. So it's basically a collection of scripts which you as a user can use. So again, only on Fritz and Alex. And the most important commands are here on the slide. So it's workspace allocate, vs allocate. You give the workspace some kind of name. You can freely choose the duration this workspace should live. If you don't give it a duration, it will be a single day. If you tell the script duration, it's up to 90 days in our configuration. Once you type in this command, it will return a path, and this is where your workspace lives. And then you can just copy data there and read data from there. If you don't know the path any longer, because whatever reasons, you can type vs find and the name you gave this workspace, and it will return the path. This is also useful when you allocate and use workspaces within a script. So you can do vs allocate with a name to create the workspace and then put the output into an environment variable and use it. And if you want to get an overview of all workspaces you are currently allocating, it's vs list. And it has a few parameters you don't really need. So just type in vs list and it will return the list of workspaces and then tell you how long they are valid for and all these kinds of things. And for more documentation, there's the link to our documentation, and there are examples and how to work with these workspaces. But why do we even have more than one file system? Why do we need it? It would be so much easier to have a single file system and all your data in one file system, and you don't have to think about it. So there are several reasons. So one reason is cost in terms of money. So having disk arrays, so HDDs, as I showed in the earlier picture with 1,000 HDDs, this is kind of cheap because a single disk is cheap and they have a quite high capacity. To build something like I showed on the earlier slides from NVMe's, it's something like a factor of 20 more expensive. So we could give you quota in terms of size or speed. So what we are doing is we have more than one system, so we can have systems with a special purpose. But this again means that you need to know which system has which purpose, and then depending on your workload and what you want to do, pick the right one. So it's basically the same as we don't have a single cluster, but several clusters, because every cluster has a purpose, and you need to know which code runs best on which cluster. So when you have data located in temp-dir, you have a bandwidth between 1 and 2 gigabytes per second, roughly, and a latency of 0.5 milliseconds. And since this disk is in your compute node, you don't share these parameters with anybody else because it's your compute node. Or maybe with a couple of jobs running on the same compute node if it's a shared node. But let's forget about that. If we go to FastTemp, so Lustre or ANVMe, we have a bandwidth of something like up to 20 gigabytes per second. I don't really know the latency, but it's somewhat slower than the temp directory because you have a network which has to communicate and things like that. But this bandwidth, on the first glance, it seems to be higher, but this is shared with all jobs running on this file system. And this can be 1 if you are lucky and you're the only one using it, but it could also be 2,000 if all nodes are occupied and all use the same file system. So it is very likely slower than the local disk. And then when we come to work, home, HPC world, these systems are, again, somewhat slower, have a higher latency. So again, if you're the only user in these systems, it might be fine for your code. But we have currently I think, 2,000 plus active accounts. So divide this number by 2,000 if everyone is active, and things get quite slow. So this is why we asked you to copy data at job start to the temp directory, because oftentimes data is read more than once, especially for machine learning, because you have training cycles and you may read over job duration the data 20 times. If you copy at the start, you read only once from the global file system and then from the temp directory. If you don't copy, you read 20 times. So the load on the shared file system is a factor of 20 higher. And if everyone is doing this, we get a problem. If no one is doing this, everyone is fine. Okay, so I already said somewhat earlier when I showed the table of different file systems that we have basically, so we have different kinds of backups and snapshots. So your data has different levels of security. As I already said, home HPC is the most secure place. So it has the most frequent snapshots, 30 minutes, and the most frequent backup. So anything which is very high value should be there, whatever that means in terms of your project. Then we have HPC Vault. Again, we have backup and snapshots, a little less frequent, but still once per day is reasonable. If you lose data, you only lose 1 day of data. So anything which is not super high value, but still worth keeping with backup should be there. Then we have work. So we don't have snapshots or backups. So if you accidentally delete something, it's gone. So yet there should be stuff which can be reproduced or just downloaded again from the internet. Then we have fast temp, so Lustre and NVMe. So this is kind of less secure because we have some kind of deletion mechanism, so data will not be resized until your project ends or your account ends. So you should have something like checkpoints or just a data set downloaded from the internet. So if you're running machine learning code, for example, you often use some kind of open source data, and this could be located there because you can just download it again if something happens. And then, of course, we have temp directory, which is only available over the period your job is running. And so it's less secure, less persistent. So just keep something which can easily be reproduced. So copy in your data, just copy it, don't move it to there, and everything is fine. Okay, I brought an example of how bad I/O can look in our monitoring. So this is just one job taken from our monitoring system. Nothing special. It's some kind of machine learning code. And let's have a look what we can see. So on the upper left, we see the CPU work which is done. And the orange part is every time the CPU is waiting for data. And as you can see, a large fraction of the time your CPU spends, or not your CPU, this job spends, is waiting for data. To the right, we have 4 GPUs which are associated with this job. And the grayish or dark part is where this GPU is working, and every white blank is where this GPU is not working. And if you look closely at the timestamps, you can see that whenever the CPU is waiting for data, the GPU stops working. Down here, we see the network communication. And we can see there are times where the network, so the NFS server, is bringing data in because no one else is using it, or the number of jobs is low enough that you get the bandwidth you need. And there are times where the server can't just feed your data fast enough. And then your GPU is waiting. So you lose time in your job because the GPU has no access to the data. And for this particular job, the data over the 24 hours was read, I think, 23 times or something like that. So a simple copy in at start would have reduced the communication over network by a factor of 20 or so. For a single job, it's not a problem, but we have 650 GPUs, so 650 jobs running. And if everyone is reading from the NFS server, it's just killing it. And this is what we see here. So this is why we recommend to copy in your data at the job start to temp directory and then use the temp directory as data source for your code. Yeah, this will reduce the load on our NFS service and make life easier for everyone. And I just have 2 links to support cases we had in the past where we analyzed the code before and after implementing intelligent data handling. And in the one case, we improved by a factor of 10 or something like that. And in the other case, it was a factor of 1.5 or something like that. But it's an interesting read, so you're invited to check it out. Okay, so I already said most of the stuff which is written on this page. So if possible, reduce the load on our shared file systems and use local storage, which can either be the temp directory, so the disk within the node, or the file system associated with single clusters, so ANME and Lustra. Yes, and for the NFS file systems, so the most harmful thing you can do is having a lot of small files. This comes from the fact, so if you have a small file and you want to read it, you have at least 3 operations which have to be performed by the NFS servers. It's open, read, close. Now think about 100,000 files, which is a low number for a training set in machine learning. So to read the entire data set, you have to perform 300,000 operations. Open, read, close, and now 100,000 times. So if you put this data into one large file, so an HDF5 data format or whatever database is supported by your code, you reduce the number of operations by a factor of 3. So this is already one step into the right direction. And the next, even better step is then copying the data to temp directory at job start, because then again, we have to open, read, close the file once at the job start. But if you have to read the data multiple times over the job, it's not happening on the shared file system, but on the local disk, and there no harm can happen. Okay, if you don't have the luxury that your code is supporting some kind of container format, so HTML5, or there are hundreds out there, depending on which code you're using. So if you can't do that, the next thing you can do is to archive the data. So put it into a tar file or a zip file or whatever archive you prefer, and then unpack this data onto the local disks. And this is more or less doing the same as having one single file copied. That's basically everything I prepared. If you have questions or suggestions, you're welcome to speak up. And if there are questions we can't answer today, you're welcome to send us a request at the email address on the slide. And one of the support staff will try to help you as good as we can.
Question about the monitoring that you showed with the NFS load versus these
let me
times.
Quickly go back to that slide.
So just from the first read characteristic from the NFS server, the lower left
Yes.
figure, I wouldn't be able to tell whether this is because the data wants to flow but can't because somebody else is using the bandwidth, or because the application doesn't need the data at that particular time. But in combination with the gaps in CPU utilization or the phases where the CPU only waits for data and doesn't do any work, that is an indication that is actually a shortage.
So from this slide itself, it's even harder because if you look closely, the time scale on the different plots is different because our monitoring does it. But so if you look here, this is roughly 1 hour and this is several hours. So basically the time scale here on the left side is zoom in on this part here. But yes, just from the network traffic, you can't really say whether or not the application just doesn't communicate at particular times or is unable to communicate because the server is not responding or responding too slow. But when you look closer, so in the CPU or GPU utilization, or as an admin look into the monitoring of network traffic, then you can say, okay, we are currently in a phase where the server is overloading and just unable to answer requests as fast as needed.
So, I mean, one of the problems is that anybody on the cluster can kind of bring down the complete system with file. So sometimes you cannot even log in anymore. So what's really the reason? So that the kernel is waiting for I/O and then everything else is blocked? Or so I just think so. What is the technical reason why someone with I/O can really make the system completely unresponsive, even if you do stuff on another file system?
I guess the answer depends. So when you speak about logging in, this is because at login, there's a script running, which is gathering your quota and telling you your quota on all the file systems is whatever. And if one of these file systems is not responding, the script is running into a timeout, but this can take some time. So for you, it seems like you can't log in because the script is not responding or the file system is not responding to the script. And then you have to wait. And after some time, the script will run into a timeout and you should get your login shell. If you are on a different file system, and so let's say someone is overloading Atuin and you are not using that file system, you should not be affected as long as you're not querying code on our file systems or something like that.
But there could be like side effects. You could have a link,
Yes.
a link in your home from your home to some location. And
Yes, of course. Because but then again, you're using Atuin.
yeah, of course, yeah. But you might not even notice.
Yes.
The link
Yes.
would be there for ages.
Yes.
You don't remember.
So it's something that could be overcome by, for example, adding a more aggressive timeout in the quota script. So I was thinking there is a real kernel reason why the systems become unresponsive.
So
When the file system
so it's not just the script. So there's a lot of things running because when you log in, your environment variables are defined. So your $home, which is pointing to your home directory, your HPC vault, which is pointing to HPC vault directories, and so on. And all these have to somehow touch the file system they are pointing to. Yes, we could reduce the timeout for the one script, but in other cases, you want to have these parameters because maybe your script is relying on them. So we might be able to reduce login problems by changing timeouts, but working with the system might still be an issue because as soon as you want to access a file system which is currently not responding fast enough, it will not respond. Or you have to wait for your LS like half a minute, or long.
And what you mean, and also Georg mentioned about the links, these are not the links which we create or we have created in the past. These are the links can be created by you. I mean, it has been done by you. Because if you don't have anything in our bash RC or something that it is loaded in the beginning at the time which we log in, then how are we affected?
So there is a central login script which is defining some parameters so that the module system is working, that all these environment variables are working, and this is creating variables linking to some place in our file systems, so your folders. And this is something we as admins did in the past, but you can create a link anywhere to anywhere, so just by ln. And
If you don't create, we will be affected. See?
yes, because how we have these parameters set up for you.
I think you should put it another way. If you're only using, let's say, $home, and $home is not affected by any,
Then you won't have issues.
you won't have issues as soon as the timeout for the initial quota
Yes.
script is over.
Yes.
If you have some
yes.
link in your home to home Saturn, and Saturn is hanging, then you're hanging.
No, you might be affected because the login script tries to set $work in an intelligent way and checks on which file service you have a directory.
But that's another timeout issue, right? At some point it will time out.
Yeah,
Not necessarily.
I don't think so.
The LS can hang for
Forever. Okay. One more reason for you to be considerate and try to implement one of these measures, not overload the file systems.
Yes, exactly that.
Would you be able to comment something on the failure rates, SSDs and PMEs or hard disks that we observe?
The failure rate, oh, that's a very interesting question. I don't take statistics on that,
Okay.
so I can't really tell you. But so we replace one HDD per week, roughly.
Okay.
And SSDs, I don't remember when the last time was we had to replace one. So it's not that frequent.
It's the other way around. Are expecting more failure rates for NVMEs or SSDs?
So because they are entirely built different, the failure rate has different reasons, kind of. So it depends on the workload you're running. So the HDDs, they have moving parts inside. So the disk is spinning all the time. The read and write header is moving across the disk. So they basically fail after a given time they were operated. And when you have a system like I showed in the beginning, you see that when you turn on the system in the first few weeks, there's rather high failure rate because disks which are of bad quality will fail quite early. Then you flatten out. And then after some years, it rises up again because you just go into aging. And at the moment, for this system, we are in this aging part. So we had a few years where we had to replace very few disks, and now it's rising up again. And this is one reason why you have to replace the system after some years of operation. And for NVMEs and SSDs, they have a given number of read and write operations you can do. So if you constantly read and write onto the disk, it will die rather early, but early is after some years. And if you don't really use it, because you don't have to do write and read operations for whatever reason, so you just don't use it, it will live quite long.
Thank you.
The failures do usually not affect the jobs.
So yes and no.
Okay.
So if the disk, which is temp directory, which is just one single disk, so there's no fallback, then your job might die because
What is it?
because it's
Interruption or something.
yeah, you might notice. It depends. So sometimes you have just a read or write error, which might crash your code, or the node will just stop responding because it has some kernel crash. But if in one of the other systems the disk dies, you will not notice it. Otherwise, you would notice that we have to turn off and on the system like once a week. So because when we build these larger systems, we have some kind of hard or software rate, so a disk can fail and another one will take over, and then you can replace disks while you're operating the system. So it's not like in your notebook where you have a single disk. If it dies, your data is gone and you have to replace the disk, turn off the system, put in a new one. We can let's go back to the picture, rather hard to see, but so behind here, there are drawers. Each drawer has 12 disks, and you can just pull out the drawer, take out a disk, put in a new one, and the system will just do it magically in the background.
So are there any requests or tickets for people asking for objects or? Because I mean, in the cloud world, it's not the standard, but it's quite common not to mount file systems anymore, but to access them via an API. So are there people requesting this, or is this no problem?
There is maybe 1 or 2 requests per year, so quite rarely. Okay, so there's a user in chat commenting that using the local disk was a game changer and made life easier.
I have a question.
Yes.
Is there any change concerning Lustre on Alex? Because it didn't used to be either mounted in the past, last year, or
Lustre is mounted on Alex. It's available on Alex.
Now, but also in the past?
Since several months, so I can't tell you when we turned it on.
But it's only connected via 25.
Yes. So it will not be as fast as the connection between Lustre and Fritz because it's not in the same network. So as you can see here, we have Lustre. So when you have Lustre in Fritz, you have InfiniBand. It's the same local network. And they are also physically located quite close to each other, so like a few meters apart. And when it comes between Lustre and Alex, you have 500 meters or so, and 2 different networks. You have to communicate over Ethernet, so it's higher latency, and the bandwidth is lower, but it's still reasonably fast. And the same is true in the other direction when it comes to ANVMe and Fritz. So ANVMe is co-located with Alex. So in Alex, you have InfiniBand, a low latency and very high bandwidth, but to Fritz, you have again to communicate over Ethernet, so things are slower but still quite fast.